Levesque, and I'll be moderating today's training. And before we do that, we're going to have a quick safety moment. As always, you want to make sure that you stay hydrated. Staying hydrated is just important in the winter as it is in the summer, so be sure to have access to water even when it's cold outside and you don't think that you're thirsty. Our presenter today is Jurek Kuzmirchek, and he's part of our amazing application engineering team. Not only does he do these red ties, but he also does customer-specific training and speaks at numerous seminars like this one. This will be next week, and this is Doble's Life of a Transformer seminar. Jurek will be speaking on physical security for transformers, so you can look this up online and attend if you're interested, keeping in mind that there is a cost to attend. Now, we appreciate you spending the next hour with us. If you like what you see, you can send your colleagues the same link you received, and they can watch it on demand. That means recorded. They can watch the recorded webinar and still get their PDH certificate, PDH standing for Professional Development Hour. Now, keep in mind the webinar audience is automatically muted, but you can ask questions at any time using the Q&A text box. If we don't get to your question, feel free to contact your local Hitachi ABB Power Grids representative, who will be happy to speak with you. Now, you can email Jurek using that link that you see under his bio, and you can discuss any possible training topics for your important issues or topics, any topics that you like. You can also contact me or connect with me on LinkedIn and keep up to date with future transformer trainings. So let's begin today's training on transformer cooling, and Jurek, I'll turn it over to you.
Thank you, Mike. Good afternoon, everybody. So today I will talk about the transformer cooling and thermal consideration in power transformers. First, why do we need the cooling equipment on the transformer? Like power transformer is very efficient electrical apparatus. The efficiency of the large transformer is 99.6 to 99.85%, and so why do we need the cooling? And the example is like when we look at the transformer, generator step-up transformer, 392 MVA with efficiency of 99.75%, we have almost 1,000 kilowatts of losses in the core and in the winding. So this type of losses will increase the temperature of the transformer inside quickly within few minutes or even sooner than that. So when we want to talk about the source of the heat in the transformer, we have two sources. Like first is the core, and in the core we have the no load losses. Every time when we energize the transformer produces the no load losses, and the no load losses have two components. One is from the hysteresis, driven by the quality, frequency, and flux density of the core. Another is due to the eddy current circulating in the core sheets. So if we want to reduce the core losses, eddy current, we want to change the resistivity, we want to change the thickness and frequency. So by changing those factors, we can reduce the eddy losses in the core as well. The other component, which is much higher, usually it's 3-5 times higher than no load losses, is the load losses. So the load losses are generated in the windings. First component for the windings losses is the I2R component, or sometimes we call it ohmic losses. Another component is the eddy losses, and usually eddy losses in the winding is 10 to 15% of the ohmic losses. And also we generate in the transformer in metallic parts like clamping structure, like tank, like turrets or cover, we generate other eddy losses. The load current generates the flux density, and with that we induce the eddy current in the metal parts, and we generate losses in those metal parts. So to make sure that we won't reduce the life of the transformer, we have to maintain the temperature limits inside of the transformer. We have to control the temperature rises, because the temperature rises affect the life of the transformer, affect the mechanical strength of the insulation system, like paper or pressboard, and also another component of the insulation system is the oil. So both those insulation systems have temperature limits, and to make sure that we don't reduce the life of the transformer, we want to make sure the hotspot rise over the ambient inside the transformer will not exceed 80 degrees C. The top oil rise will be limited to 65 degrees C. And those temperature rises are based on the 24 hours average rise, ambient temperature of 30 degrees C. And the temperature limits for the temperature rises may change if we see that the ambient temperature is it's higher, or if the elevation of where the transformer is installed is higher than 3,300 feet. So the absolute temperature limit for the hotspot in the windings is limited to 130 degrees C. This is with the assumption that the transformer has thermally upgraded insulation paper. And top oil for the normal loading is limited to 105 degrees C. We designed the transformer to meet the temperature limits for emergency loads, and during those events, the temperature limits are much higher. For long-time emergency loading, the temperature limit for the hotspot is 140 degrees C, and for short time, it's limited to 180. But at the same time, with much higher temperature, the aging of the transformer, the life expectancy of the transformer can be shorter, and at the same time, with much higher temperature, we may see some gases generated during those events. So, loss of life. By increasing the temperature of the hotspot, we change the loss of life. We reduce the loss of life of the transformer. So, if we increase the hotspot by 6 to 8 degrees C, we may reduce the life of the transformer by factor of 2. And basically, on the conductor, we have paper insulation, and paper insulation has something which is called like a chain of the polymer chain, and this is the length of the chain in the cellulose fiber. Normally, the new transformer has DP in the range of 1,000. After 30, 40, or 50 years, DP goes down, and at the end of the life, DP is 200 or less, which means that the mechanical strength of paper insulation is much lower, and we may have a problem with the mechanical strength or short circuit strength due to the paper conductor being weak at this point. We can increase the temperature limit by using different different type of paper covering or different material for the insulation. So if we change the paper on the conductor to a high temperature material, we can increase the hot spot rise to 90 degrees, or in some cases even to 115 degrees. At the same time, the absolute temperature limit will change from 120 to 130 or even 155 degrees C. And here are some details about different insulation system. So with full hybrid insulation system, we have high temperature insulation on the winding conductor between the turns and discs, and in the oil ducts, in the vertical oil ducts next to the windings. In mixed hybrid insulation system, we have only high temperature insulation in the area where we see that the temperature is much greater than in other locations. So usually it is on the top of the winding. So the paper conductor in this area is high temperature material, the same as the spacers. And then another example of different insulation system is the semi-hybrid system. So in this case, we use only high temperature insulation tape on the conductor. And then high temperature insulation system has, in the high temperature insulation system where the hotspot temperature, permissible hotspot temperature is 155 degrees C, we have solid insulation like paper and spacers and winding insulation made of high temperature insulation, and also the transformer is filled with mineral, with ester fluid. Because with ester fluid we can go to higher temperatures. Now, the winding temperature rises. How the temperature of the winding change with the height of the winding? On the bottom of the tank, the temperature of the winding and oil is the temperature of the oil in the tank and oil in the winding is pretty much the same. But when we go to the top, the tank oil temperature is several degrees lower than winding oil temperature. It is because the winding oil temperature is next to the heat, next to the source of the heat, which are the windings. And at the same time, when we look at the distribution of the losses in the windings, we see that on the bottom, in first few turns or first few discs, and the same, and on the top, we have much higher losses. Those losses are driven mainly by the radial eddy losses due to the radial component of the flux. And with higher temperature on the top of the winding, and also with the much higher losses in the first few turns or first few discs, we see that hotspot always is located somewhere on the top of the winding. It's either first or second turn or disc from the top. In smaller windings rated for smaller MVA, or where in the windings where the current density is rather low, we use only vertical oil ducts around the windings to dissipate the heat, to reduce the temperature of the windings. But in the main windings, like high voltage, low voltage windings, in those windings we have much higher losses, and also the radial build is much greater. So the vertical oil ducts are not sufficient to dissipate the heat. And we designed the zigzag oil flow circulation. So every several discs or turns, we install the oil guides inside and outside. And with this solution, we force oil to go in between the discs and between the turns. And this will reduce significantly the gradient between oil and the windings. But in the design, we always have to make sure that when we design the insulation system, we consider the reduction of the cooling surface area in the parts of the windings covered by the spacers, by the axial ribs. And also we have to make sure that the oil is not restricted by the insulation parts. Dissipation of the heat in the transformer. We have conduction, convection, and radiation. So with the conduction, let's say we have inside the disc or inside of the turn, the conductor which is inside has usually much higher temperature, and due to the difference in the temperature between the turns or between the turns and the insulation, we have the heat transfer. The heat energy is transferred from the conductors which have higher temperature to conductors which have lower temperature. Convection. So with convection, when we have the heat source as a winding, the heat from the winding increases the temperature of oil, surrounding oil. And with the higher temperature of oil, the density of oil goes down. And this creates natural circulation in the transformer tank. Similar phenomena we see between the radiators or coolers and air. So radiators having higher temperature change the temperature of increase the temperature of the air, surrounding air, and with higher air temperature, the density of air is reduced, and then we have better circulation. We produce circulation around the radiators. And radiation is basically the transfer of heat energy by the magnetic wave, and it's we transfer energy with the radiation from the tank and from the cover. The size of the cooling changes significantly with the rated power of the transformer. The losses increase much faster than the cooling surface of the transformer, and for larger units, the tank is not sufficient to dissipate all heat. So we add the radiators, and we add the fans, then we add coolers, we add pumps, because we have much higher losses. We produce much higher losses in larger units, and we need a more efficient cooling system. Now we can look at the different cooling classes. So we have oil natural, air natural, very common in the smaller transformers. And this is, I would say, maintenance-free solution. We don't have to really do any maintenance on the rod, or the maintenance is very limited. Then we have another solution where we want to improve the circulation of air around the transformer. So we install the fans on the radiators, and then with oil forced, we have a solution where we force oil going to the tank, and in this solution, we install the pumps between the cooling system and the tank. The pumps force oil circulation in the transformer. Very similar solution is with the water coolers, where we force oil going to the tank, but the difference is that we use a different type of heat exchanger. So we use water coolers. On one side we have hot oil going in, and then on the other side we have cold water used to dissipate the heat. And then we have very efficient solution where we push the oil directly into the winding. We pump oil directly to the windings, and in this case we reduce significantly the gradient between windings and adjacent oil. And we can have this solution with pumps and oil-to-air coolers, and also we could use oil water coolers as well. Now we will go more into the details for each particular cooling solution, and we can see that we can combine radiators with the pumps and also coolers with radiators. Radiators with the pumps and fans with the radiators and pumps. So, as I said, on with radiators is very common on the smaller transformers. We use only natural circulation of oil and also around the transformer, natural air circulation. And by changing the location of the radiators, we can improve the heat exchange between the radiators and the air. So this will reduce significantly the oil temperature in the tank. And with this solution, we can reduce the size of the cooling system. However, in some cases, we have to be careful because this solution is very sensitive to the location where we have high seismic activities, and it could be very difficult to provide sufficient bracing for high seismic accelerations. To improve the air circulation around the transformer, we install the fans, and in this case, most of the time the transformer has on-and cooling only up to 60% of the rated power, and then we have two additional stages where we turn on fans, like first stage of on-off cooling, when we turn on the first group of fans, and then at the full MVA, we turn the second stage of the cooling. And the cooling is controlled, the fans are controlled by the temperature gauges. We can combine radiators, fans, and pumps together. So by adding the pumps to the circuit, we change the oil circulation. We force oil into the tank, and at the same time we change the temperature of oil. And by changing the top oil temperature, we can affect the temperature of the hotspot. We can reduce the temperature of the hotspot, and we can also reduce the size of the cooling system. And at the same time, we can have a transformer loaded to most likely 60% of the rated capacity without fans and pumps running. But with this solution, we add one more device, which is the pump. And then it is similar solution to the one before, but we use different, instead of radiators, we install the oil-to-air coolers. And with this solution, the size of the transformer overall dimensions and also the amount of oil is reduced. But we may significantly increase the auxiliary losses due to the coolers, the power the power needed by the coolers, and also it is this solution affects the maintenance. And right now I will talk about the solution where we have oil forced into the tank, and then we have water coolers. So we have to use, in this solution, we can reduce significantly even more the cooling system, but we have to make sure that we have sufficient source of water with sufficient flow of water, so we can dissipate the heat generated inside the transformer. ODAF cooling we can use in the transformers with radiators and pumps as well. So in this case, oil from the radiators is pumped into the chamber located under the windings, and it is pushed to the windings. And as you can see, the top oil temperature, or the temperature rise at the top and the bottom of the tank, is very similar. The difference is only 5-8 degrees. But at the same time, by going with the directed oil flow into the windings, we can reduce significantly the gradient from the windings to the oil. And the same solution we can have with oil-to-air coolers, but the difference is that we don't have on stage. So basically, when the transformer is loaded, the cooling system must be on and running. And this is the solution with oil directed and water coolers connected to the transformer. So this is very common solution in hydroelectric plants, because we have easy access to water. Now, a little bit more why we see significant difference in the gradient for transformer with natural oil circulation and in the transformers with directed oil into the windings. So the gradient between the winding and the adjacent oil has two components. First is the conductive part. This conductive part is driven usually by the thickness of the insulation on the conductor. And it is the same as it is pretty much the same as we see for ONAN and ODAF cooling. But with change to the ODAF type of cooling, we significantly reduce the convective part of the gradient. So overall gradient between the windings and oil is much lower. And you can see how the gradient changes and how the top oil changes in the transformers with natural oil circulation. Usually the gradient on the top of the tank, or top oil temperature rise on the top of the tank, is much higher than the oil temperature rise on the bottom of the tank. For transformers with directed oil flow, we see very little difference. Usually it's in the range of 5 to 8 degrees C. And also the gradient between the winding and oil is much lower in transformers with OD cooling comparing to the transformers with on and off cooling. So advantage and disadvantage with OD. Normally we have the OD cooling is much more efficient. We can control the hotspot better way. We can use smaller oil ducts. We can sometimes reduce the noise level because we will use less fan. We can reduce the size of the transformer. We can also use less materials, but we have to be careful because if we change the current density, if we increase the current density, we may have a problem with the mechanical stresses during the short circuit. And then disadvantage is that the transformer must have cooling on when it's energized. Only the solution with radiators will allow us to load the transformer without fans or without pumps running. But most of the time when we have oil-to-air coolers or water coolers, the transformer must be, the cooling system must be on all the time since when the transformer is energized. With the pumps, we have additional losses. We increase also maintenance, and also the change. We have to design the pressure chamber. We have to design the piping inside of the transformer, so it changes of the design. And with those additional parts, we increase the labor, and this can increase also production time of the transformer. So far, I talked mostly about the core form transformers, but the temperature limits for core form transformers and shell form transformers are identical because we use the same insulation material. So in shell transformers, we also have to control the hotspot because the temperature of the hotspot will affect the aging of the transformer. But construction of the shell form transformer is completely different than core form. So the oil circulation inside of the windings is completely different. The windings, which are called pancakes, have much lower oil velocity in the horizontal parts on the bottom and the top of the winding, and this affects the temperature in those areas. So we could have situation that the transformer, shell transformer, has on stage, but if we increase the rated power or load on the transformer, we have to use directed oil flow. We have to push oil into the windings with certain velocity because we have a significant part of the windings where the natural oil circulation is restricted. And here it's a comparison how we can change the cooling system on the shell transformer, how we can change the size of the transformer and oil volume by changing the type of the cooling. So you can see that with the same load losses and no load losses, we can significantly reduce the oil volume and the total weight of the transformer. Yeah, so this is the same design, but the cooling system, the same design of the active part, but the type of the cooling system is different. So in the third column, we see transformer with ODAF cooling only, and the total weight of the transformer can be reduced by 44 tons. Many times the hotspot in the windings is monitored by current transformers, but this solution does not give does not use direct measurement. It is called thermal image. So to measure directly the temperature of the hotspot inside the winding, we have to install fiber optic probes inside the spacers between the first few disks, and this gives us the actual temperature of the hotspot. Knowing this temperature, we can manage the loading of the transformer, and we can also connect the temperature, the fiber optic, to the monitoring system, which will allow to calculate the loss of life, and also will allow to load the transformer when we really need it in emergency situation. Now I will talk a little bit about the cooling retrofits. So why do we have to do the cooling retrofits? Mainly because the cooling system, existing cooling equipment is failing. We may have a problem with leaking radiators or fans or pumps failing. In some cases, we want to increase the rated MVA of the transformer. We have concerns with noise, so we want to change the coolers to new ones which produce much lower noise. And those are the main reasons why we do the cooling retrofits. What do we have to consider during the retrofits or before? First, we have to understand the current condition of the transformer. Like we have to understand how this transformer was loaded in the past, what is the actual aging of the transformer, what is the moisture content, and what is the current condition of the bushings and other components. Then, and it is important, especially when we have to when we want to increase the rated MVA of the transformer, we have to really know the design of the transformer. We have to know the design of the winding, leads, internal connections, because by increasing the MVA, we increase the current density in the windings and the leads, and this will affect the aging of the transformer. We have to also check the performance of new cooling system, especially when we talk about the OD cooling, when we can face the streaming electrification. And then during this modification, we may have to install new bushings for higher current. We may have to install some additional brackets for the cooling system, change the conduits, install additional contactors or devices in the control cabinet, or even add one more control cabinet because the existing one is just too small. We may have to even modify internal connections. And in some cases, we may want to even consider the adding of the monitoring system like DGA, online monitoring system. I said, I mentioned about streaming electrification, and this is phenomena which involves the separation of the positive and negative charges at the interface of oil and press board. And it depends on the oil velocity, surface of the material, temperature, moisture, and type of oil. Basically, when we increase the oil velocity, we increase the probability of streaming and electrification. And with separation of the charges, we may have a high concentration of positive or negative charges in one area, which can start the partial discharge. And this can cause even a failure of the transformer. So when we talk about the retrofits transformers with OD cooling, we think that if we provide pumps with much higher oil flow, and then we improve the situation. But we have to really remember that we must know the design, and we must know the velocity inside of the active part, because we may create something which will cause the failure of the transformer. So every cooling upgrade, like especially when we talk about the change in the rated MVA, requires design evaluation, and we have to consider not only new coolers, but we have to look at the bushings, we have to look at the tap changer and internal connections. We have to recognize that some modifications which have to be done to the control cabinet as well. And then as a summary, I just want to say that the cooling is really critical for the performance of the transformer. And when we change the winding hotspot, when we increase the winding, the hotspot of the windings, temperature of the windings, we can significantly reduce the life of the transformer. Also, selection of the cooling system has to be optimized. Sometimes we may change the cooling system because we have limited footprint. We have a foundation which cannot take larger load, so we have to change the size of the cooling system. And also, it is important to verify that cooling system works properly. So every time when we do the transformer testing, it is recommended to also test the cooling system. It is recommended to perform the heat run test, even on the duplicate units, because we may have a case where the oil circulation in the windings is restricted, and this will affect the temperature of the windings and the hotspot. And also with the cooling retrofits, we have to remember that we have to really look into the design of the transformer inside, not only the replacement of the cooling system from the outside, but also inside. And this is the last part of the presentation. So now it's time for questions.
Great. Jörg, thank you for that excellent information, really detailed, really enjoyed it. And as a matter of fact, we do have a lot of questions that have come in, quite a few questions. And if you have any questions, you can be sure to type them right into the Q&A text box. I'm going to take these questions and put them on the screen, Jörg, in no particular order. And the first question is what is the most reliable type of cooling?
For me, it's cooling with radiators only, because even with fans, some of the fans may fail or will fail over the time, and so for me, cooling with radiators is most reliable on cooling.
Thank you. Next question. We'll keep the flow going here. Question asks, if you upgrade the transformer's NVA and add cooling, does it decrease the expected life of the transformer if done at half-life?
So in this case, we have to know the design. We have to know details of the design of the windings of the core, because if we increase the NVA, we have to verify the temperature rises. And sometimes we think that we will increase the cooling capacity. We add more coolers or larger coolers, but it may be not enough to reduce the temperature inside of the transformer. So we may, with the upgraded, with the higher NVA of the transformer, we may increase the hotspot temperature above the permissible limit. But when we do the upgrade of the NVA, we always have to go back to the design and check and run the temperature calculations. That's why it is really recommended to, let's say, to go back to the supplier of the transformer who have access to the documentation of the existing transformer.
Thanks, Yurik. Next question is a bit of a fun one, and I think it raises a little bit of all of our curiosity. And this question asks, I've always wondered if spraying water, like from a fire hose, on the tank or radiators during extreme heat or possible overloading, is this effective or a waste of time?
I would say it's kind of dangerous, because electricity and water do not work well, so we can spray water all over the places, and this can cause external discharge from the bushing, and no, I don't recommend. Do not do it.
Excellent. All right. Well, stay safe. That's thanks for addressing that. And let's keep going. The next question asks, is there a rule of thumb when forced air or directed oil must be used? I'm sorry, forced oil and directed oil must be used.
No, there is no rule of thumb like we use the radiators and fans on very large transformers, and we use the coolers and pumps on very small transformers like 50 MVA or 20 MVA. And the type of the cooling is really driven by the size, the permissible size of the transformer or weight of the transformer. If we have limitations for the total weight or total size of the transformer, we go with more efficient type of cooling like forced oil or directed oil.
Good, and we're going to keep pushing through these questions here. We'll get as many as we can. Thank you for submitting them. Next question is there a maximum duration associated with emergency operation of transformer operating at high oil temperature?
Yes. So in this case, it is really good to have the fiber optic probes inside of the transformer, so we will recognize where we will recognize the actual temperature much faster. And but overall, during the emergency loading, we have to limit the top oil temperature to 110 degrees C. But at the same time, we have to watch the temperature of the windings. We have to watch for the temperature of the hotspot. And in some cases, most of the time, the temperature of the hottest spot could be the limiting factor.
Okay, thanks, Eric. I like this next question. Of course, we have some very hot, sunny areas. And the question is, how do you consider solar incidence in your design?
I think this is about solar flares, and so we do the evaluation, GIC evaluation for the transformers, and every time when we see the request, we look at the requirements for the DC current induced by the solar activities, and we check the impact of this DC current on the temperature of the transformer and basically loading of the transformer. And at the same time, the solar activities and DC current may increase the sound level as well. And some of the designs can take some of the designs like three-legged core are not so sensitive to solar activities, but some of the designs like five-legged or shell transformers can be more sensitive to the solar activities. And we do this case by case.
Thanks for the clarification. GIC standing for geomagnetically induced currents. Thank you, Eric. Next question I will put up front here on the slides. And the question asks, can you use RTDs, hot spot, top oil, and ambient, to reliably control fans at desired temps to extend the transformer life?
Yes, and this solution has been used for a long time. So we can use RTDs. We can use those devices to control the cooling system, operation of the cooling system. And basically, we can lower the threshold points, so the temperature, the fans will turn on at lower temperature, which may extend the life of the transformer.
Thank you, Eric. Next question. Keep plugging along. I see we only have a few minutes left. This question asks, in case of OD cooling, when current density in the windings can be increased, does it affect the aging of the insulation or transformer life?
So the aging of the transformer is affected by the absolute temperature, and in this case, for OD cooling, we don't change the temperature, permissible temperature for the hotspot, and also aging is affected by moisture in oil or inside the transformer or in the insulation system of the transformer. So if we control the temperature and if we control the moisture inside the transformer, we won't reduce the life of the transformer, even with higher current density.
All right, thank you. And this next question, I'm pushing out here to our slides. The question is, on a cooler, for example, with one pump and 4 fans, if one pump is not working, how efficient is a cooler? If one fan is not working, how efficient is the cooler?
So I prefer the second option. So if one fan is not working, we still have pretty good cooling for the transformer. But if we have pumps, if we have pump which does not work, and blocks oil, we have to de-energize the transformer right away because there will be no cooling, or only cooling left on the transformer will be through the surface of the walls and cover.
All right. And let's see if we can keep going here. Next question, what is it? Matter of fact, Eric, we have gotten a lot of questions concerning temperature rise. This one says, what is the difference of a transformer 5565C temp rise compared to just 65C rise?
So the rated MVA of the transformer at 55 degrees C rise is reduced by 12%. So there is a factor of 1.12 when you recalculate the rated power of the transformer. By going to 65 temperature rise, you can increase the temperature, you can increase the rated capacity of the transformer by 12%. And this dual rated capacity of the transformer comes from the time when we didn't have thermally upgraded paper, and we had to reduce the temperature of the top oil and the windings to 55 degrees C, and hotspot temperature was reduced by 15 degrees C to 65. But at 65 degrees C, we should have the same capacity, the same MVA of the transformer.
Thanks, Eric. We have about 90 seconds left, and I want to be respectful of everybody's time. We do have a lot of good questions in here, and some of the questions do mention that it could be a long answer. So what we'll do is we'll gather these questions at the end of the webinar, and although it may take some time, we'll do our best to reply back to those questions that you ask. I'll also ask, if you can, please fill out the survey. It's a very simple survey, and we use those answers to make sure we improve for future webinars. And you can see the resource list that is there towards the right side of your screen. You can download today's slides, and you can find our webpage that has all of these red ties on demand. On demand means that you can watch them, recorded webinars,